Ribs play an important role in a wing structure. They help introduce local loads into the rest of the wing structure, but they also protect against skin buckling. But what does this buckling actually look like? And how does the number of ribs affect how it occurs? How do engineers decide how many ribs to put in a wing? I'm thinking a testing demonstration would be the perfect way to see for ourselves. And luckily, I have a few friends at the Delft Aerospace Structures and Materials Lab to help me out. Let's go over our setup first. We unfortunately don't have the tools or time to make a full wing, so we'll make a wing box, which will have all the elements of the wing structure that are contained within the front and rear spars. I'd like to test 3 conditions: one wing box with no ribs, one with 1 rib, and one with 3 ribs. This should give us a good idea of how ribs affect the strength and buckling of the wing box. But first things first, we have to build them. Measure once, cut twice. Measure twice, cut once. Measuring, cutting, drilling, riveting, it's a lot of work. But finally, everything is being put into place and we're almost ready to go. While they're finishing up the construction, let's take a look at our test setup. Our wing boxes will be placed in this specially made test rig. The box gets clamped on both ends to make sure it doesn't move around during testing. One end of the box will be attached to a rack and pinion gear system. When the large wheel is turned, it slowly pulls that end upwards and applies a load to the wing box. Eventually, the wing box won't be able to withstand more loading, and at this point, we consider the box to be failed. And now it looks like we're ready to start testing. The first test is the wing box with no ribs. We'll speed things up a bit so we can get to the fun part. Next is the wing box with 1 rib, and finally, the one with 3 ribs. If we look at each test individually, it's difficult to see exactly what's going on. If we look at a side view of the clamped end of each box side by side, we can see some differences, mainly that each box buckles differently. This is interesting, but I'd like to know a bit more about the exact differences. Thankfully, we're engineers, so we have a few tools that we can use to help us out with the analysis. Before testing, we spray painted a random speckle pattern on top of each wing box where it was clamped. Try playing connect the dots on those ones. During the tests, 2 cameras positioned above the setup took pictures at short intervals. Afterwards, specialized software tracks the movement of each speckle from image to image. This is then translated into a heat map of sorts, showing us where deformation is occurring on the surface of the wing box. This process is called digital image correlation, or DIC for short. Now, if we put the DIC results side by side, we get a lot more information than from just the first videos. Here we see 3D models of the root section of each wing box, no ribs on the left, 1 rib in the middle, and 3 ribs on the right. If we look at the deformation at failure, the difference becomes clearer. The wing box with no ribs seems to crumple up and there's a slight large inward dent. Those deformations are pretty big. It wouldn't do well in flight, that's for sure. In the wing box with 1 rib, there's a similar dent, but there's also one that pops up outwards nearby. However, the magnitude of the deformation is lower than the wing box with no ribs. We seem to be getting somewhere. Finally, let's look at the wing box with 3 ribs. We see the same upwards and downwards dent in the panel, but the deformation is even smaller than in the 1 ribbed box. Buckling is still occurring, but is not nearly as severe. What do you think would happen if we added more ribs? I'll leave that question up to you to think about. For now, what can we conclude from our wing box demonstration? We can see that ribs play an important role in minimizing skin buckling in wings when they're loaded in flight. And in flight, maintaining the aerodynamic shape of the wing ensures that air will flow smoothly over it.